Hello. In this video, I'm going to talk about some of the basic antiderivatives. I want to begin to become more specific about how we actually use our differentiation knowledge to allow us to calculate antiderivatives. The antiderivative of a function really is just the process is just differentiation gone backwards. So a good place to start for looking for basic antiderivatives is to go to our table of key derivatives. Now, if we go back to our summary of differential calculus, you'll remember we had a table that looked something like this. For each function f in the first column, we've written its derivative in the right-hand column. So the derivative of sine is cos, the derivative of tan is secant squared, the derivative of a constant is 0, and here we have the derivative of x to the m is mx to the m minus 1. Now, for antidifferentiation, we're going to start with this right-hand column. That's what's given to us, and we want to move to the column on the left as our answer, as our antiderivative. So to do that, all we really have to do is switch the two columns. So now we have a table of antiderivatives where we've got a function f here, and then on the right-hand side now we have an antiderivative. So in this table, the derivative of sine is cosine, so the antiderivative of cosine is sine. And we just use the same derivative table but going the other way to give us our basic antiderivatives. There's one change I've made here. The row that corresponds to x to the m, it's useful for us to put x to the m over here in the this column. So what the other table has is mx to the m minus 1, and it's more convenient for us to rewrite that row. So the antiderivative that I'm writing for x to the m is 1 over m plus 1 x to the m plus 1. The derivative of that function is x to the m. And this table goes down a little bit. You'll find that if you download the script for this particular video, it'll have this table in it. And it really is just our table of derivatives, but reversed with the order of the columns reversed. So how are we going to use this? And I'm going to do a few examples now. So the table tells us that the most general antiderivative of x secant squared x is tan x plus a constant. So this integral sign without any limits on it stands for the most general antiderivative of what I've got inside here, the integrand. So then to evaluate the integral from 0 to pi over 4 of secant squared x dx, we just use this antiderivative, evaluate it at pi over 4, and subtract the value at pi equals of tan at 0. So the tangent of pi over 4 is 1, and the tangent of 0 is 0, so that integral evaluates to 1. Notice that the integral, the first one here, integral of secant squared x dx, is actually standing for a class of functions, whereas the definite integral, 0 to pi over 4, where we have limits on the integrand sign, integral sign, that evaluates to a number. The next example is to start with the antiderivative of 1 over x, and we know that is log x. That comes out of our table, and that's just a very simple fact that we proved about the derivative of log x, that it is 1 over x. And so the integral from 0 to 3 of 1 over x dx can be evaluated by the fundamental theorem of calculus as the logarithm of the top limit, 3, minus the logarithm of the bottom limit, which is 2. And if you use your calculator, you get this number, 0.4055, as the value for this definite integral. So definite integrals evaluate to numbers, indefinite integrals evaluate to functions plus a constant. Now you'll remember that that integral also represents a geometric fact. The number is that we calculate is the area under the graph of y equals 1 over x between x equals 2 and x equals 3. So here is the graph y equals 1 over x, and I've shaded the region under that graph between 2 and 3. And so this integral is evaluating the area of that region. And that area we calculated as 0.4, and we can see it's an area of width about width 1. The left side is 1/2 and the right side is 0.33. So that's a reasonable number to get for the area of that region. So each definite integral is calculating an area of some region. And the third example, I'm not going to work on more than to simply write down what I have here. The indefinite integral of 1 dx is x plus a constant. This is a basic integral that we need to have, and it's simply saying that if you take the derivative of x with respect to x, that's what the dx is for, you get 1. Our approach to integration is to take our arbitrary, our integral that we're trying to evaluate, and we use reduction techniques to split it apart and reduce it down into simpler and simpler integrals, where we eventually want to get down to the most basic kind of integrals, and we hope that eventually by using all of our reduction techniques we can eventually get to one of the antiderivatives in our table of key antiderivatives. And one of the key antiderivatives that you're going to reduce to will be 1. And if you have to realize that once you get to a 1, the antiderivative is just x. Let's wrap this up with a brief summary. A definite integral can be calculated once we have an antiderivative of the integrand. So that turns integral calculus into a general hunt for antiderivatives, and we have lots of techniques for finding antiderivatives. What we know about derivatives can help us a lot when we're looking for antiderivatives. In fact, we're going to develop a series of techniques for integration, which are really just each of the basic rules, product rule, chain rule, etc., of differentiation turned on their head and run backwards. It's important to remember that the indefinite integral notation with no bounds on the integral stands for a function plus a constant, whereas a definite integral, where we have limits on the integral sign, that represents a number, which is a different kind of thing.